Hello everyone and a very warm welcome to the Aspire Pilot PPL theory course. Today we're going to begin with meteorology and this is going to be first in the series, so let's get into it. Now the objective of these videos is to be quick and just to give you some basic knowledge to help you pass the exams. It will go through a few in-depth detail. I don't expect the video to be much more than half an hour as we can cover things fairly quickly and get through it nicely. I chose to do weather first because I think it's the most interesting subject. It combines facts and science together. It's combined quite an interesting subject that you can use in everyday weather, whether it's planning for your barbecue or your parties, or whether you're going on a long drive or flying, being that we're potential pilots in the very near future. It is quite an important subject, so without further ado, let's get into it. You can just have a little look there. We'll start with the atmosphere, set the scene, and then we'll go through winds, clouds, fronts and icing, and all them things will lead us to understand the forecast and the weather charts themselves. So let's begin. We'll start with the atmosphere, and I'll go very quickly through this. To help you pass your exams, all you need to know in this bit is that the troposphere is from 0 to 10 kilometres, about 36,000 feet there, and that contains all our weather. You won't go out of this unless you train to fly in the space shuttle, so which I don't think even the Cessna 152 will climb as fast as that. That was a joke, by the way. Anyway, so yep, we've got that in the way. The greenhouse effect. The way we need to interpret this to help us pass our exams is to understand how the atmosphere is heated up, and that's that the sun's radiation, the solar radiation I should say, is absorbed by the Earth's surface, and then it is emitted back into the atmosphere and emitted by the Earth's surface, and this is what heats the atmosphere, like the greenhouse. There you go. So the proportions, that's another thing you need to get handy with, is you need to know the proportions of the gases in the atmosphere themselves. So 78% nitrogen. Unlike popular belief, you'd think there'd be more oxygen because that's what we breathe every day, but apparently not. It's 21% and the others is 1%. So we've got that. Now, the coldest time of the day is just after sunset. Now you can sort of just think that through. You think the sun's beating down all day, then overnight it's being emitted by the Earth's surface again. You get the coldest time just after sunset, just before the sun starts to heat the ground again. And you can see this is sort of the diurnal variation throughout the day, and the diurnal wind change is due to, you get a sea breeze because the ground absorbs less heat and in turn heats up the air above it a lot more, and you get this flow of air, where like a convection current that you done at middle school. Now, the very reason we do get weather is because the uneven heating of the Earth. Now, because the Earth is a sphere, flat earthers disagree if you will. You shouldn't be here anyway if you don't have the intelligence to be a pilot if you're a flat earther. I don't want to offend anyone, but it's up for good discussion there. But anyway, the Earth's a sphere, it's get heated by the sun, and of course you get more heating at the equator than you do at the poles. This causes uneven distribution of the heat on the sun, on the Earth I should say, and then you get movement of air to try and equalise this. Air overseas picks up moisture, goes over a hill, causes rain and so forth. So there you go. It's all down to the sun. So around the atmosphere you get this thing called the International Standard Atmosphere. Now this is what's considered to be just the standard atmosphere, just for random. It's not so much random, but it's usually for comparison for actual data. Now at ground level we assume that the temperature is 15 degrees, the pressure is 1013, and the density of the air is 1,225 per cubic meter squared, cubed. Now, in the commercial world, we can use this to make some performance calculations, but usually we just use this as a rule of thumb to make some quick basic calculations for the PPL syllabus. Now, the temperature is 15 degrees and it falls 2 degrees per 1,000 feet, which means at 2,000 the temperature is 14, and I'll get there eventually, 13, and 2,000 it is 11. The pressure is, in the lower levels we count it to drop 1 hectopascal per 30 feet, and we can use that to make some quick calculations for QFE, etc. So what is the EASA temperature at 5,000 feet? This might be a little question you might have pop up, and to work that out, it's just 2 times 5 times 10. Take that away from the EASA ground level, and you get 5. So that's quite straightforward there. Just read through if you didn't quite get that, and you'll soon see why the answer is 5. So altimetry. Look at this quick. Assuming that you've got a basic grasp of what these is, QNH is the altitude above sea level, and QFE is the height above the ground. Now, atmospheric pressure decreases with height, and in the lower levels we assume that this decrease in height is around 1 hectopascal per 30 feet. So a quick calculation that you can do is that the QFE, you can sort of make some quick calculations for that. So a simple way to do it would to look at the airport elevation, say 300 feet, and look at the QNH, and then use them to derive a QFE figure. So if the QNH is 1013 and the airport elevation is at 300 feet, well, assume you start at sea level and you go up 300 feet, the altimeter would just display 300 feet on the QNH. Well, you don't want that. You want to wind it down to QFE. So to get that down, you just divide the airport elevation by 30, which is how much 1 hectopascal is gains as you gain altitude. You get 10. Take that away because you want to get that needle going back down, because it would be at 300 if you get what I'm saying, and you get 1003. You might get a combination question. So at airport A, the QNH is 1020, and it's 200 feet above mean sea level, and airport B, the QNH is 1010 and 220 feet above mean sea level. So if you flew direct from A to B at aircraft A, the aircraft is at 5,000. Well, at airport B, because the QNH has dropped, the aircraft will be lower. So in actual fact, 10 hectopascals difference will cause a 300 feet difference, so you'll be 300 feet lower, so you'll be at 4,700 feet. And the height above the ground, well, because the height above mean sea level at airport B is 220 feet, you take that away from what we got, which is 4,700 feet, and you get 4,480 feet, so it's all quite simple there. And that last part of that question, we just applied the same calculation to what we done towards the end of the part 1. So with warmer air, as you can see, what will happen is that as you fly into, it's probably easier if we assume that we go into colder air to start with. If you fly into colder air, then the altimeter is going to overread and you'll be lower than you actually think you are on the altimeter. If you fly into warmer air, you'll be higher than you think you are because the actual instrument in the cockpit will read lower. The altimeter will underread, and yeah, you'll be higher than is actually indicated on the needle there. So these are things that you need to just remember for the exams. In real life, I'm not so much you really need to apply that math at this level anyway. So winds. So I'll just check that. There we go. I haven't missed anything. So the main thing you need to remember for the forces is that the geostrophic wind and the gradient force. The geostrophic wind, as you can see on that diagram, is the wind that flows parallel to the isobars. Now, when it flows around curved isobars, it's known as the gradient force. And this is combined. Pressure gradient force, you need to remember, flies from high to low. It goes from high to low because it's pressure gradient, pushes from high to low pressure. And the Coriolis force is the effect of the spin of the Earth, and those two give a resultant force, which is the geostrophic wind parallel to the isobars and gradient wind when it flows around curved isobars. By Ballott's law, this is just for the exams. You're not going to stand in the garden and do this, and this is some prat. Mm, It's just a thing that you need to remember for the exam. But if you in the northern hemisphere, if you stand with your back to the wind, then you'll have high pressure on the right and low pressure on the left. And low, left, both begins with L, so that's a simple way to remember that one. The wind in the northern hemisphere again, if you increase your height, the wind speed will increase and increase with heading as a rule of thumb. So if the wind is at, say, 20 knots and the heading is 200 degrees, then at 2,000 feet it might be 220 degrees and 30 knots. So it's all just taken into perspective there. And the last two things, just quickly, anti-clockwise winds flow around a low pressure and clockwise around a high pressure system. Mountain winds, you do need to be careful of these because especially on the downwind side of the hills, you will get rotor winds and so forth. So I've got some questions there, just pause the video now and just see if you have kept up. And then if you're happy that you've got all that information, then we can continue. What is the EASA temperature at sea level? Well, that's question one. What is the EASA temperature at sea level? It is 15 degrees for EASA. Question two, QNH 1020, local field elevation is 240 feet. What's the QFE? 240 divided by 30 is 8. Take that away from 1020, 1012, you get. Where does the heat energy from in the troposphere come from? Well, it's radiated heat via the Earth's surface from the sun. You have 1013 set, you fly into a colder region, will the altimeter overread or underread? It will overread. When is the coldest part of the day? It's just after sunset. What is the Earth's temperature at 5,000 feet? 5 times 2 is 10, take that away from 15, you get 5. What layer of the atmosphere does the weather occur in? The troposphere. What is the definition of water vapour? I didn't cover this so much, but just so you're aware, you might get questions you're not so sure of, that's why I put it there. In the simplest way, it will be multiple choice. So if you think about it, it's a gas that condenses and forms cloud. So there might be a little outlier, and you can be well aware of that because it is multiple choice. Right, so cloud formation, the fundamentals. So in day-to-day life, without any clouds, there's water vapour in the air, although it is in gaseous form. However, we have this thing called the dew point, where it changes states and it condenses. The air condenses into a certain temperature into a liquid form. And in meteorology, we have this thing called relative humidity, and it is the ratio of water vapour in a parcel of air to the total amount that it can carry. So I think there's a little thing you need to be aware of for the exams is that warmer air can take more water vapour than colder air. Now the explanation to this is quite complex, so I won't go into that, but that's just a little thing you need to remember. But once it reaches 100% relative humidity, you get this change of state, and this is known as the dew point. 100% relative humidity is the dew point. So just remember that the relative humidity, it's not just humidity, but the relative humidity is the ratio of water vapour in the parcel air compared to the total amount that parcel can carry until you get to 100% relative humidity and you get dew form. So low humidity, it might be very dry air, but high humidity, you might start to see some condensation in the air itself. And just at the bottom there, you've got, I put DARLR, I can't even say it, the dry adiabatic lap rate, and that is assumed to be 3 degrees per 1,000 feet, so it's a dry parcel of air. The ELR on the right hand side is what we've done before, it's just the average lapse rate between the saturated, which is 1.5 and 3, and the adiabatic lapse rate. If that's more than 3 degrees per 1,000 feet, we assume that the air is unstable. That means it has a good tendency to rise, a vertical motion. So now we get on to the pretty bit. Now you can start to see some fairly common names in here. Now just for the exam purposes, Nimbo, if you see in both of those it's raining, so Nimbo means rain bearing. Cirro or Cirra, means high up. Middle is alto. Strato is flat. So you can just see the combinations there. And cumulo or cumula is cumulable. You get sort of woolly, cotton wool, heaped forms of cloud, and this is what you get. All good so far. So this is a lenticuliform cloud, and this forms above a hill or a mountain. And as the for this to form, you want stable, moist air. So you might get something from the southwest in the UK flowing over the Pennines, for example. And as it goes over the hill, it's sort of got an arch form. The wind sort of follows an arched path over the mountain caused by the shape. And as it reaches its peak, this is where it will reach its dew point we just saw. This is what it will start to cool. The adiabatic substrate means at a certain level it will be cooled enough to condense and form clouds. And it gets this shape, like a bit of a UFO, because the shape that the air is flowing over the hill. Now, you think, if you're flying a glider, rising up on that flow of air over the hill is great because you can ride the wave, they call it. But for us GA pilots, if you fly downwind, you get quite a lot of turbulence as this air sinks and starts to tumble over the hills. So you do want to avoid these clouds if you see them, especially on the downwind side, although they are quite lovely to view as an observer. So the real ones to avoid, much more than lenticular clouds, cumulonimbus. These form in warm, moist, unstable air with a rising action, so it might be orthographic lift from hills, or it might be strong thermal, especially in the summer in Eastern Europe. You get a lot of these form where you've got this warm and moist, unstable air. Particularly if you think of the UK, if you've got that warm and moist air coming in over the Atlantic or from a low pressure system, you've got this warm air, it's really unstable, rising really quite fast, and you get these clouds start to form. And the most dangerous part of these, you get them start to form, they might develop from a cumulus into a cumulonimbus and start to grow as they suck in air from the sides. But the most dangerous part is a mature stage, because you've got all these hazards associated with them at this mature stage, which includes severe icing. From 0 to minus 20 degrees, you might get wind shear throughout them, especially this is one of the reasons you shouldn't really fly into them or near them, because the air is being sucked into this, drafted in from the side like a big convection current pushed out from the side. So you've got wind shear even if you're near them. Downdrafts from this sort of rising and sinking motion, severe turbulence, and you're going to get lots of rain and hail potentially, and really, really heavy, nasty downpours, and they are quite nasty clouds, and even for airliners they cause quite big delays and problems. So you do really need to be careful of these big, nasty clouds. Don't fly near them, and certainly don't go in them. But just to recap, the most dangerous part is the mature stage, and severe icing you can expect from 0 to minus 20, and wind shear, downdrafts and severe turbulence are the main points that you can cause problems. Yeah, that's probably going to be one of the more embarrassing crashes if you ever encounter one. Obviously you can't prevent some, but if you do fly near some bad weather, particularly cumulonimbus, and you crash, well, that's your fault. Silly thing to do, and that's how you will end up. So the last part of clouds, you just need to be aware of fog. Now, you don't really need to know too much about the fog in detail. That's just good to know. Clear conditions, sort of in a nice clear sky, you can expect this radiation fog to form on a clear night, as I said, with light winds and high humidity. Now the name gives it away because the Earth is losing so much heat, it's actually cool in the air near to it. Reaches dew point, and lo and behold, you get fog as this starts to condense. And particularly on a clear night with light winds, 5 to 7 knots they like in the exam. Just a little tip there, just so it mixes up and just the turbulence keeps it rather than just sitting there. It forms a nice layer, and high humidity, so you've got plenty of moisture to cool into a thick fog layer. Advection fog, you can get slightly more stronger winds than with radiation fog because it's already flowing. The actual reason it causes fog in the first place is that this warm moist air is being cooled over a surface such as a river, usually a river or a sea, and that's known as advection fog. Warm moist air flowing over a cold surface. And frontal fog, you can expect in advance of a warm front, just where the colder air is saturated by warm raindrops, which occurs just as at the front of a warm front, really, as it evaporates. So we'll just do a quick progress check. So warm, moist, I'll give you time to pause the video. Let's begin. Question 1. Warm, moist, unstable air is likely to form what type of cloud? You can expect cumulonimbus for that. Wind 280 at 12 knots at L3. What would the wind be at 2000? Well, you increase speed and increase heading, so you're looking at 300 degrees and about 17 knots there. What does balance law state? Well, standing in the garden with your back to the wind, the low pressure's on the left and the high pressure's on the right. In a cumulonimbus cloud, where can you expect serious icing? Well, when, I should say, but you can expect it when it's 0 to minus 20 degrees Celsius. Clouds above 20,000 feet are cirro. If you just have a look there, we'll get there. Cirrocumulus, cirrostratus and cirrus, the higher level ones there. What is the wind flowing around curved isobars? So it's the gradient force. The ones parallel are the geostrophic, but the ones flowing around curved isobars is the gradient force. When is frontal fog most likely to form? In advance of a warm front, where the cold air is saturated by the warm raindrops. When is radiation fog most likely to form? Well, on a clear night, with light winds 5 to 7 knots and a nice high humidity to get that dew starting to form in the air. So that's all good. So fronts, air masses. Now I'm not going to spend much time here because it's really simple to remember. All you have to remember is polar is cold, tropical is hot, maritime is moist, continental is dry. Put them together and you get your answers. Unstable and stable, you don't really need to worry too much because they're all different anyway. So when I do the answers, you'll be able to go through there. But just as an example, tropical means warm, maritime means moist, so you put them together, the air's warm and moist. There's your answer, nice and simple. So fronts. So to start off with, we'll go through our warm front. Its symbol is a red semicircle. You can see it in the top left there. And a warm front is where you get this warm air mass sort of sliding over a colder air mass. Warm fronts are slower than cold fronts, and they have a shallow slope of 1 to 150. The weather that you can expect is fairly drizzly, fairly longer lasting, sort of dreary, nasty, sort of depressing day. You can sort of usually see these coming because, as you can see there, they've got such a slope and difference in weather. Get warmer as the air comes in because you've got the warmer air mass coming in. So it does get warmer, although the weather gets drizzly. And behind you sort of get this formation of stratocumulus, which makes it just all say grey and overcast. To begin with, you'll see the cirrus start to form, then the cirrostratus, and then followed by the stratus and the nimbostratus. So it starts off fairly light, and you can actually see it. A couple of weeks ago, I actually saw this in action. Just stayed at home, you start to see the formation, and lo and behold, I looked on the internet, and it was a warm front. So you can usually see these coming. Cold front. So a cold front is a much faster moving system. They've got a steeper slope, so they last not so long. Storm Eileen, as you remember, I think one of the cold fronts, part of that must have lasted, what, you could actually see the front itself, it must have lasted all of 2 hours, but they've got a steep slope, 1 to 150. Colder air, which undercuts the warmer air, and you get thundery weather. This warm, moist air is being lifted, and that causes a recipe for some nice thunderstorms or some cumuliform cloud. And lastly, you get this faster cold front which catches up the slower warm front, as we saw before, and as these combine together you get this warm moist air lifted right above both of these, and as they cool quickly you get this warm moist air again being lifted, and thunderstorms are possible. But also the combination, the danger might be you might get some stratiform clouds sort of mask these embedded thunderstorms, which do make these occluded fronts a little bit more dangerous to us pilots because embedded cumulus clouds are harder to see. So fronts, highs and lows. Excuse my joke there, but yes, anticyclones are the happy moment, so to speak, because they bring some very nice weather. High pressure, which means you get sinking air. The winds flow clockwise around the isobars. So that's just one thing to remember. Contrary to its name. You don't get any fronts associated with a warm front so much, which means you get lovely dry and clear weather. It's more longer lasting, so if you bike on your commute to work and you don't want to put your waterproofs on, you can usually put those away for a week, especially in the winter. In the winter, but the weather's usually bad otherwise. You can get quite happy with these. They sit over the UK for at least 3 or 4 days, usually maybe around 5 days to a week. And in the summer, they bring warm, clear, really quite nice weather. In the winter, you can expect some frosts, just because the weather will be clear with no clouds, and you might start to get that radiation fog that we mentioned before. And sometimes with a little bit of wind on the edge, it might start to lift and form some stratiform cloud and might actually cause quite a dreary day. However, these fogs usually go on. It's quite a nice day. It might be a little bit colder than a cloudy day, so to speak, in the depression. However, a depression is fairly depressing, as it says in its name. It's a low pressure system, so you've got rising air, unstable air. The winds flow anti-clockwise around the system because of the sort of the cloud and the motion of these, the rising air, so to speak. You get these fronts attached to it, so you get these strong winds around the curved isobars, and you get lots of precipitation, but they do pass through a lot quicker. I think Storm Eileen last week must have lasted all of about half a day. Those people shooting it like they did in America must have scared it away. That's not the real reason, but just so that's always a good thing if you can associate something with, for example, a depression, like Americans shooting it away, so it'll go away very quickly, and it always helps to remember. But it's probably a little bit far-fetched, that one, but hey, let's continue. So finally we'll finish with some icing before our next check. So we'll start off with the left. I just mentioned rain ice first, most likely to form above a freezing level in cold air before a warm front. So you're above the freezing point, but you're in cold air, and before a warm front, and it's in the rain, and you expect this to form on the aircraft. And if those water droplets start to flow across the surface of an aircraft, you get this clear ice form, this like clear sheet, as you can see on that picture on the car there, start to form. Rime ice forms when the supercooled droplets of water form onto leading edges of an aircraft. It's sort of a semi-opaque, sort of translucent, or whatever they call it, and usually forms on leading edges of an aircraft. And then last but not least, hoarfrost. Now this is not an ice, it's more of a frost, but it occurs when moist air comes into contact with a frozen surface. So you get these longer strands because all this moist little droplets build up into form these longer sort of, they sort of break little dust. It's quite dusty. And carb ice is the last thing we'll look at. Well, carb ice is most likely to form in warm, moist air at low power. However, it's been need to form in all weather, so just be careful there. You always want to be doing carb checks every 20 minutes or whatever your instructor says, but just be aware of it on all weather. It has been known in all weather, but it's most likely to form in warm, moist air at low power settings. So the final progress checker before we combine everything into some real world situations. I'll just let you pause the video now. Excellent. So what front in its slope occurs when a warm air slides over cold air? You get a warm front as this angle of warm air slides over a cold air, and its slope is 1 to 150. Flying below the freezing level in rain, what type of icing can you expect? Well, it says it in the name, rain ice. It should be above the freezing level in advance. What is it? In advance of a warm front, but that's the definition, because in rain, that's the most common thing you can expect. What properties does a polar continental air mass bring? Well, as it says in the name, polar and continental, it is cold and dry. When flying towards a depression, what drift can you expect? Well, if you imagine the wind flowing from 12, it's anti-clockwise around the depression, so imagine the wind flowing from 12 to 6 on the clock, and you approach the clock at 9 o'clock, while the wind's going to blow you towards 6, which is to the right, so right drift. What conditions does a summer and winter anticyclone bring? Well, I don't think we really need to distinguish between the two too much, but just remember that it's usually clear and dry, no cloud formation. In the winter it's a little bit colder, with some potential radiation fog, and it is calmer winds and no frontal, so that's the reason why. What properties does a tropical maritime air mass bring? Tropical and maritime means hot and moist. When is rain ice most likely to form? In event of a warm front above the freezing level in cold air. When is rime ice most likely to form? Well, you can expect rime ice when you've got these super cooled droplets forming on the leading edges. So combining all these, you can actually start to look at Metar. Now, it's always worth, beyond this video, just go through all the different symbols. If you type in Metar symbols, you can look on all the websites and start to learn and remember all these points. Although, if I go through an example TAF on the right and an example Metar, you'll just start to get the format. So the first one is Echo Golf Mike Charlie, which is South End. And you see it says 152120 Zulu. That means that it's on the 15th, whichever month it is. It happens to be September, and the time is at the forecast, but not the forecast, the time when this Metar was put out, or the weather was observed, is at 9:20 Zulu, which in the summertime is an hour behind, I believe. So if the wind is at 300 at 3 knots, you can see there 300 degrees at 3 knots. So the wind is coming from 300, and the weather is cav okay, which means the ceiling and visibility is okay. So the visibility is greater than 10 kilometers, and there is no significant clouds to affect anything. It's pretty much clear. The temperature and the dew point. The temperature comes before the slash, so temperature is 10, but the dew point is 8 degrees, and the QNH is 1012. That's the Q. The Q is QNH. The next one's got 9 and 9 and 9 and 9 in it, which means the visibility is better than 10 kilometers. If it was, say, 7,000, then the visibility would be 7,000 meters, because all horizontal distances are usually given in meters. And then scattered there, you can see, means that there is scattered clouds at 2,400 and 3,400. And the last one is an automatically generated Metar. So you can see that there it says NCD, which means no cloud detected by the automatic system. So there's no, it's sort of similar to cav OK, but it's just done by an automatic weather system. At the top there, in the black, we have a TAF. This is one we had Storm Eileen, actually, and as it stands, so at the top you'll see that you get a main sort of overview of what you can expect, and then below you get all the different temporary parts between them two times. So at the top it says TAF Echo Golf Sierra Sierra 12 16 52. So it was on the 12th. This TAF was released at 12 on the 12th of September at 16:52 Zulu. And as you can see, it says 12:18 to 13:24. So between 6 p.m. and midnight. 6 p.m. on the what is it, Sunday, 6 p.m. on the 12th to midnight on the 13th. You can expect the wind to be 200 at 14 knots and the visibility to be greater than 10 kilometres and the clouds to be scattered at 3,000. However, it doesn't end there. You get temporary forecasts within that time. So you can see you've got a load there. I'll just go through the first one. So it says 12:19, 12:24. 20018G28. So it means that the wind between 7 and midnight on the 12th is expected to be 20018, gusting 28 knots. Visibility is 7,000. You can expect moderate rain and broken clouds at 1,400. And the prob bit is the probability that this is going to happen is 40%. So yeah, that's basically what they mean. And the becoming bit, the BEC-MG, it just means that afterwards it's becoming surfaces. So the one there where it says 1301, 1305, it then says that the wind will be becoming 260 at 14 after that period. So later in the day it's becoming certain, following on from that temporary forecast. So that's that covered. Like I said, just remember them symbols, see if you can just go through them, and that's the general format that you'll expect to see. So the last two things are different charts that you can expect. Now this is the form 215 and it gives you an overview of what's happening across the UK. You can expect that you can get this from the Met Office GA subscription, and I think most flying schools have access to this at their office anyway, so if you want to practice this you can get them to print off a few, because they usually have these available to have a look at before the day. But in the exam you'll just need to have a basic grasp list, and if you look in the bottom left hand corner you've got everything laid out there. So if you look at that you shouldn't have too many problems, because you can sort of just, if you look at everything you can make your way to understand it all, just by using basic common sense and things and using the symbols to help you. However, the things you just want to be aware of, if you see that trough in the top left corner on the right, you can see that it's moving at 5 knots to the south, and that's just basic things like that. And the different winds, so you've got 10 knots, 20 knots, different winds that you can expect. Yeah, so what you can expect throughout the day. So it says that 30 kilometres is the surface visibility in area A, occasional 7 kilometres in showers of rain, so it's really quite easy to read. The cloud that says area is scattered, broken, and just these are quite difficult just to get a really good idea of what's going to happen, but it's just an overview of what you can expect through the day. So it says in B it's widespread broken, overcast. You can expect icing and turbulence from 8,000 to 10,000, isolated embedded cumulonimbus from 15, from 1,500 to 3,500 to the surface, to the above the chart level, and just little things like that. But I've just done that by looking at the bottom left, so you can just use these. And there will be in the exam parts will give you a little example flight, and it will say, well, if you're flying this, what do you need to be aware of? Well, if I was flying in area A, I'd have to be wary of the isolated showers of rain and thunderstorms, and the turbulence and ice and above 8,000, and just little things. So if you look in the area and just look what's there, it will say, is the flight safe? Well, yeah, if you avoid the thunderstorms, just things like that. But there will be multiple choice, so there will be one example. And if you look at the bottom, it will say heavy showers or thunderstorms largely becoming confined to the sea coast, otherwise similar. So that's just a basic overview. So you can say heavy shower largely confined to sea. So in the afternoon you can be sure that the flight is safe. So it's just your judgment really of what you think. If you can see in there, in area C on the chart on the right, it says 25 kilometres, nil weather, isolated in 7,000, isolated hill fog, isolated turbulence and isolated heavy turbulence. Occasional scattered and broken cumulonimbus, 4,500 to isolated scattered broken and upslope. So apart from hill fogs and bad weather on the hills, that should be fine for the flights on there. So my judgment would be that it's okay to fly. And lastly, you want to look at form 214. Now, this is the other form you look at, and your flying school will usually give this for your planning purposes, for your wind, for your plogs and things. But if we just look at, what one shall we pick? In the top left, 60 north, 0730 west. If you look there, in the left, you've got 010205. This is the altitude, so 1,000, 2,000, 5,000 feet respectively. And then you've got the wind direction, so 360, 360, 350 degrees. Then you've got the wind speed, and then you've got the temperature at them levels. So that's simple as that. And yeah, so if they ask for you that what's the 2,000 foot wind at 60 north, 0730 west, well, it's 360 degrees at 25 knots, and the temperature is 5. So it's as simple as that. So I hope you enjoyed today's video, and I hope you got a lot out of it. If you do have any suggestions for further videos, what can be improved and what can be changed, do let me know. From here, I suggest that you use the PPL Tutor app to practice some quizzes to make sure you just go over this stuff and get competent with it. But apart from that, best of luck with your exams. I'll do anything to help you on our Facebook group, and thank you very much for even watching the video in the first place. So I do appreciate anyone's support, and if you do have any suggestions for the next videos, please do let me know. Apart from that, best of luck with your exams, and have a lovely morning, day or night. Best of luck, guys.